Hello, chemistry students. In this video, we'll be discussing the nature of light and its wave characteristics. So I'm starting this video with something we're all familiar with, and that is lightning. And we all know that we typically see the lightning before we hear the thunder. In fact, you can even sometimes count the number of seconds as a quick little anecdote, and for every second, it's roughly a mile away is what they say. So why is that? Well, if we look at light, it travels at a certain distance per time, meters per second. And we see that it's 3 times 10 to the 8 meters per second. If we look at sound, it's substantially slower. Well, how much? If I was to put this into exponential notation, it would be 3.40 times 10 to the second power meters per second for the rate at which you hear the sound wave. So that difference of 10 to the second and 10 to the 8 is a million times different. So that just gives you an idea of how much faster light travels. So that is a constant. And that constant of the speed of light, if you round it, it's 3.00, or if you want to be a little more precise, 2.998 times 10 to the 8 meters per second. That constant is denoted by C for the speed of light. You may be familiar with this constant, as many people are familiar with the equation E equals mc squared, where energy is equal to mass times the speed of light squared, which, by the way, is kilograms per meter second squared, which is equivalent to 1 joule. So why do we talk about light when we study chemistry? Well, chemistry is all about ratios, but it's also all about movement of electrons. It's the movement of electrons in the valence shell that results in bonds being broken and bonds being formed. And that's what we observe with chemical reactions. So our electrons, the way they're organized in the atom, is really important because it's going to tell us certain properties, both physical and chemical, based on these electrons and where they're located in their valence shell. So we'll see that the reactivity and the arrangement of the periodic table is related to electrons in future videos. But this video is focusing on light. So we have to understand that electrons are incredibly small. A single speck of dust has more electrons than the number of people who have ever lived on Earth. That's how small electrons are. Electron behavior determines the behavior of atoms. And in chemistry, we need to study this electron behavior, but they're so small. Directly observing an electron in an atom is pretty much impossible. It's so small that observing it actually changes its behavior. So this led to a lot of problems using classical mechanics or classical physics to explain the behavior of electrons and atoms themselves. Even shining a light on the electron would affect it. So to develop a further understanding of electrons and atom, quantum mechanics were developed. Now, the theories of quantum mechanics that were used to explain the electrons are devised by certain scientists that you may be familiar with: Bohr, Schrodinger, Planck, and Einstein. And just to show how even the scientists who've created this theory to bridge the microscopic level to the classical macroscopic world, to kind of show you how challenging it was for even the people who devised it, I put a few quotes here. Schrodinger stated, "I don't like it, and I'm sorry I ever had anything to do with it." It's Schrodinger's equation, which is called the wave function, which is a mathematical model that predicts the location of an electron with 90% probability. We call these locations orbitals. So we use that to help describe the shapes of where electrons are located. God does not play dice with the universe. This was actually Einstein's quote in his disbelief that something such as the atom can really rely heavily on probability as opposed to determined characteristics. There's indeterminacy in the study of electrons. So in a way, this is kind of funny because here's Einstein talking about its disbelief. So why am I talking about electrons when I said in the very beginning, this is a discussion for light? Well, it all started with light. Light interacting with atoms is how we ended up understanding electrons and developing our quantum mechanic models. And it helps us understand the organization in the atom. So light is not a form of matter. It is electromagnetic radiation, shorthand EMR, and it is actually how energy travels through the universe. So when we think of light and electromagnetic radiation, there's really two perpendicular fields. There's the electric field and the magnetic field component. Now, when we're studying electrons, we're pretty much going to focus on the electric field component because that's what's interacting with the electrically charged electron. So in many of your classes, when you see wavelength, they only show the single wave as opposed to both perpendicular waves. And that single wave is showing in chemistry, the electric field component. So we're going to take a look and we're going to describe this wave in terms of wavelengths. And wavelength is basically the distance between peak to peak or trough to trough. It's one full cycle of a wave. You could even describe it as node to node. So wavelength. What about amplitude? Well, amplitude, many of you have heard, is the vertical height of the crest from the midline. So here's my midline. The height to the peak of this crest is considered amplitude. Or you could actually pick from the midline to the trough. That's considered the amplitude. Again, wavelength, which we use the Greek symbol lambda and is measured in length, we use the unit of meters, is the distance between waves between one cycle. So now when we're looking at different colors, we're actually observing different wavelengths. So when we think of visible light, the range of wavelength is anywhere from 740 nanometers to 390 nanometers. So a nanometer is basically requires 10 to the 9 nanometers to equal 1 meter. Again, we're using nano as a metric prefix, and it's 1 billionth times smaller than a meter. So we see that the wavelength in red light is longer than the wavelength in blue light. So what does that mean? Well, it just determines light, and we're going to refer this also to frequency and energy in a moment. But when we compare it with amplitude, don't get confused. It's not the amplitude that determines the color of the light. The amplitude only determines the brightness. So the lower the amplitude, the more dim the light. The higher the amplitude, the brighter the light. Now, what about frequency and wavelength? So frequency is per second. We use this new Greek symbol, and the per second or hertz is basically the number of cycles of waves per second. So you can think of it as me basically picking a reference point in space. And in 1 second, how many of these peaks, how many of those cycles pass this reference point per second? Now, this is kind of a cheesy drawing, so we can look at it in terms of this. We can see that if I have a wave and they're traveling at the same speed, the ones with the longer wavelengths are going to have less peaks passing a point per second because their wavelengths are further apart. So a longer wavelength versus a shorter wavelength, you can clearly see that the shorter wavelength is having more peaks pass per second. So when we're looking at frequency and wavelength, they are related. Now, how are they related? Well, if the wavelength is reduced by a factor of 2, then the frequency increases by a factor of 2. So what exactly does that mean? In 1 second, if the wavelength is reduced in half, the frequency will double. And this represents, here I see that it's 2 hertz representing 2 peaks passing per second in this reference point versus 4 hertz, 4 cycles per second. So we see clearly that we have wavelength. And how is it related to frequency? Well, if we increase wavelength, so this is an increase in wavelength, frequency decreases. So it's clear that they are inversely related. So how do we make this proportionality equal? We need a proportionality constant. We need a constant that can convert wavelength, which is meters, and these per seconds into each other. So what can we use? Well, we can use the constant speed of light. Now, why would we use that? Well, if we take a look, the speed of light is in units of meters per second. And again, if I look at wavelength, that was in meters. We said frequency was in hertz or 1 per second, which we see that the speed of light is meters per second. And there's that constant that we talked about. Now, how can we use that? Let's say I want to compare the wavelengths of 2 different waves at different frequencies. So we have 93.3 megahertz versus 93.3 kilohertz. A megahertz is 10 to the 6 hertz. So the first thing I want to do is I want to convert everything in terms of per seconds, because then I can use that equation that I used earlier, that the speed of light is wavelength times frequency, to solve for my wavelengths. So I can rearrange this by dividing both sides by frequency, and I can plug in my constants. Here I just rounded, but I plug in the 9.33 times 10 to the 7 per seconds, and I see that the per seconds canceled, leaving me with 3.22 meters. So this is my wavelength for this frequency in megahertz. So when I look at kilohertz, it is a kilo is 10 to the 3 versus mega 10 to the 6. So if I have a smaller frequency, what should happen to the wavelength? Well, I see that I get 3.22, but now it's in kilometers. So what does that show me? Higher frequencies have shorter wavelengths, or you can think of it as a shorter wavelength is going to have more cycles pass a reference point per second than a longer wavelength. So long wavelengths have low frequencies and short wavelengths have high frequencies. And that goes back to that relationship that the speed of light is wavelength times frequency. So when we think of the electromagnetic spectrum, a lot of people are only thinking in terms of a very small portion, and that's visible light. And that's because, that's how we see color. Now, a way you can remember the visible light region is the acronym Roy G. Biv. It's what we see in a rainbow. We have red, orange, yellow, green, blue, indigo, and violet. And what we notice is the red light is longer and the violet is shorter. And we see in terms of wavelength, here they have nanometers. We see that this is roughly 700 nanometers, this is 400. Now, what is shorter than visible light, where our eyes can't really process this particular wavelength? It's not long enough to stimulate the receptors in our pupils and cones and rods. Well, shorter wavelengths are within the ultraviolet region. So shorter wavelengths are shorter than the violet light in the visible spectrum. And the shorter wavelength is ultraviolet. And we know that ultraviolet, too much of it, can actually cause skin damage. It actually can excite electrons and actually break bonds. That's why ultraviolet, too much sun, is dangerous. So what's even shorter than ultraviolet? X-rays. Now, X-rays are actually so small they can pass through most substances, but not dense bones. That's why we use them as an imaging tool. But if you've ever had an X-ray, what do they have you do? They have you put on that lead apron to protect your organs so that that form of energy doesn't cause any damage. Now, what's even smaller is gamma rays. Now, gamma rays is basically, you typically see this when unstable radionuclides decay, and it's usually accompanied with the release in energy from an atom, okay? So this is extremely small, okay? We're talking picometers. So the gamma rays wavelengths is picometers. So what we're seeing is we're seeing really small wavelengths on this side, okay? So what does that mean? If they have really small wavelengths, they're going to have higher frequencies. But we also know, and I'm kind of setting us up for the next video, that things like ultraviolet, X-ray, and gamma rays are very energetic. So the smaller the wavelength, the higher the frequency and the higher the energy. So they have more energy. So the smaller wavelength results in higher frequency and more energy. Now, if I go on the other side of the visible spectrum and I look at what's on the other side of red, well, it's longer wavelength and we have infrared. Now, infrared is typically, you can think of it in terms of thermal energy. So you could have like night vision goggles and things emit infrared in the form of thermal energy. You may have even witnessed this if you're taking a long road a trip and you're looking down the highway and it's hot asphalt and you see, they call it a mirage. You see the squiggly lines and you think you're having a mirage, but that is a thermal energy. You can actually sometimes even see that shadow because the particles are moving faster. And even though you don't see the actual light of infrared, you can see the shadows of the particles. Now, what's a little bit longer than infrared? Now we're getting into microwaves, and that's where you have radars and satellite, and it's a way of heating the food because microwaves can actually vibrate bond energies and cause vibrations in your food. And even longer, and now we're getting to the kilometers wavelengths or radio waves. And radio waves are basically how we transmit energy or communicate between different stations and emit signals, electrical signals, because we're dealing with electromagnetic radiation. So I hope you enjoyed this video and it helps you understand the properties of light, which are amplitude, wavelength, frequency, and how we've focused and related it to different forms of electromagnetic radiation, and for our next video when we discuss energy. Thanks for watching.